Well, we've already checked out some solution strategies that we need for solving some forms of nonlinear equations. For example, Bernoulli are nonlinear, and some homogeneous equations are nonlinear, and separable equations could be nonlinear, and maybe some exact equations would be nonlinear. So many times you can't solve them explicitly, but this section and the next couple give a not necessarily numerical approach involving substitutions and as well as power series. So let's look at this. Let's try to look at solution by substitution, or the types of equations we can solve this way. Yes, focus. So nonlinear second order differential equations with the dependent variable y missing, as well as with the independent variable x missing, can be solved using the substitution u equal y prime. So here's an example of each of these two types. So here's one with x missing. We'll do in the next video one with y missing. So we wanted to solve y plus 1 times y double prime equals y prime squared. So if we just let u equal y prime, then y double prime is du dx, which is dy du times dy dx, and we call dy dx, since that's y prime, that is u. So that's u times du dy. And then we'll substitute into the other equation. Okay, and when we do that, we get y plus 1 equals, this would have been y double prime, but now it's u du dy, equals y prime squared, so that's going to be u squared, because we said u is y prime. So now that we have this situation, we can divide both sides by u. That'll cancel this u out and one of these u's out, and we'll just get y plus 1 times du dy equals u. And now we can separate the variables. So when we do that, dividing both sides by u and multiplying both sides by dy and dividing both sides by y plus 1, we get du over u equals dy over y plus 1. Now we integrate both sides. ln absolute value of u equals ln absolute value of y plus 1 plus c. Got to be a constant on both sides. We'll just combine them and make it this one constant. And then when you raise e to the ln absolute value power equals e to the ln absolute value of y plus 1 times e to the c. Well, there's the e to the c, and here's y plus 1, and here's u. Now I'll grant you, since we had absolute value, that technically should be absolute value and absolute value of y plus 1, but the e to the c is an arbitrary constant, so that will cover the plus or minus. And since it's just another constant, let me call it c1. So we get u equals c1 times y plus 1. But that's not a solution. Solution would be y equals something or other. Well, we don't have that. But we do know that u is y prime. So now, if we replace u with dy dx, then dy dx equals c1 times y plus 1. And guess what? This one's also separable. Divide both sides by y plus 1, multiply both sides by dx, we got dy over y plus 1 equals c1 dx. And now, you integrate both sides, you get ln, absolute value of y plus 1, equals c1 times x, integrating this, but then plus a new constant, new arbitrary constant, we'll just call it c2 for lack of any better constant to call it. So now that we've got that, we can make both sides exponents for e, and then we get absolute value of y plus 1 equals e to the c1x times e to the c2. So, and if we do that, we'll make the e to the c2 equal this constant c, and then absolute value of y1 equals this constant c times e to the c1x, but notice that since this is an arbitrary constant, that takes care of the absolute value around the y plus 1. So finally, if we subtracted that 1 from both sides, we get y equals c, which is really e to the c2, but that's alright, it's just an arbitrary constant anyway, times e to the c1x minus 1. And I only denoted this. This is just a different constant from this one. That's why I have a subscript on it. So that is the solution for our equation. And we've got it. Okay.